Assalamualaikum warahmatullahi wabarakatuh. My name is Nasrian Saputra, and this video I will review journal A Big Data Architecture for Security Data and its application to phishing characterization. This journal made by Pedro H.B. Las Casas, Vinicio Santos Diaz, Wagner Meira Jr., and Dorgival Guedes. They are from Computer Science Department, University Federal de Minas Gerais. Okay, first we will read the abstract. As the internet grows, cybersecurity problems also arise. Different types of malicious activity has been explored by attackers. However, the existing defense mechanisms are not able to completely end the malicious threat. Versus phishing this continuous arm race. The development of applications to mitigate those threats presents some complicating factors, such as the growth in amount of data and the variety of data that can come from different sources. In this paper, present an architecture built on top of big data framework that aim to mitigate cybersecurity problems such as spam and phishing, and we show how it is being used to study spam and phishing collect using a global honeynet. The next page we will read the introduction. According to McAfee, the likely annual cost of cybercrime to the global economy is more than $1,400 billion, and the cost of cybercrime include the damage to company performance and national economy caused by cyber attack, and the effect of information theft. As reported by McAfee in 2013, this type of incident include more than 14 million people in us. One estimate put the total at more than 1,800 million individual record in 2013. To face such attack, we need to be able to identify and characterize them. A complicating factor in this case is the enormous increase in the volume of available data that has happened in recent years. Almost 90% of data in the world today were created in the last 2 years alone. And every day, approximately 2.5 quintillion bytes of data are created. Security issues become more critical due to factors such as the large volume and variety of data that may be vulnerable. The diversity of data sources and formal, and the velocity in which data are generated, typically following a stream natural with a high volume. Enterprise usually collect terabytes of security relevant data, including network traffic and software application, even among others. The use of big data framework for security solutions presents several benefits, such as the possibility of storing and using large quantity of security data. Also, analyzing log, network flow, and system even has been used for several decades in security solutions. Conventional technology are not adequate to apply on such long-term, large-scale volume. Traditional techniques are inefficient when performing analytic and complex query on large, unstructured dataset, while big data platforms perform test operation efficiently. However, so far solutions have been tailor-made, making their experience hard to adapt to other contexts. In this paper, we present an architecture for cybersecurity application based on big data framework. Our architecture has the capability of collecting data from different sources, storing, combining, and processing them effectively. For example, sources like pcap file and other log from a honeynet, data stream collect from blacklist sites and security relay, search stream from social network like Twitter, can all be stored in our system. Different algorithms, possibly implemented in different programming environment, can then be used to process combined data from different sources as needed. To illustrate its use, we implement an application to process large volume of spamming traffic collect from all the world. Our application collect data from honeyspot located in different countries and combine and store the message in mailbox of top HDFS. In that way, all security related data In that way, all security-related data become available to application using Hadoop and Spark. The main contribution of application is its capability to identify phishing email instead of spam message using natural language processing and locality-sensitive hashing. To inspect the text present in the message, we were able to detect different phishing campaigns. Evaluating the performance of the application, our experiments show that our tool presents a speed up of 8.7 and 13.17 in a cluster with 9 machines using Hadoop and Spark, respectively. After the introduction, now we will move to architecture. We propose an architecture for cybersecurity system and use it to implement a spam analysis application to identify phishing campaigns. The architecture must satisfy important properties when considering a general large-scale application that are scalability. The performance must be scalable as input data grow. Efficiency. Since it aims to deal with security threat, major property is the ability to analyze the data efficiently, being able to mitigate the proposed problem as fast as possible, and uniform programmability, in which the architecture must be able to deal with multiple kinds of data types and from different sources. The architecture is depicted in Figure 1. It's composed by 5 parts. First, data collection, and second, storage, reader, processing, and visualization. As you can see in this Figure 1, data collection. The first step of architecture is collection of data. The most important aspect of this step is to identify relevant data source. In our example application, the goal was to analyze spam traffic. So we used two low interactive hotspots installed around the world as data collector. One of the main advantages of using honeypot to study spam is direct interaction with the agent responsible for to abuse, making it possible to capture important information about it. The honeypot used in this work emulate open proxies and open mail relay machines on the network that are traditionally abused by spammers. For each connection received by the honeypot, we stored the full content of its message with original header, as well as additional network information extra at the time of the connection, which were stored as a stand header for each message. The collect message stored in mailbox. B. Storage. Considering the heterogeneity of data that can be used by an application, it is important to have a storage strategy that will maximize performance and facilitate the use of dataset. Every data source has different characteristics and is produced in a different volume and velocity. Thus, this is important to be considered in order to store them in the best possible way. One of the most used data storage in HDFS, it is reliable and scalable distributed file system that provide high performance access to data. One important aspect of HDFS is fault tolerance, which is obtained through replication, keeping multiple replica of each data block in several different nodes. Another important aspect is that is directly accessible from most big data processing framework. C. Reader. Once the data is properly stored, we must enable the processing tool to process the input data to guarantee scalability. HDFS is designed to allow parallel access to large files, so that different processing elements can work in parallel, reading from different parts of file. The first step for that is partition the data in large 128 MB block. which may then be stored in multiple machines. If that blocking pattern happens to break a logical record across two blocks, the SDFS API must include enough information about the file data type to reconstruct this record. Hadoop environment offers several input formats, which go from simple line-based to JSON file. Unfortunately, some data frequently used in the security analysis, like VCAP file and mailbox, are not treated to the standard API. To avoid that, our architecture includes an SDFS extension for mailbox. Ordinary core reader use a regular expression to identify the beginning of an email, and follow standard mailbox formatting rules to identify its header and the message content, building an object for each message, each even across file block boundary if necessary. A similar product may be applied to other important file types, such as PCAP and NFCAP. As we split a logical partition into record, our architecture may reader extra information about the email to be used in the processing phase that allow, for example, that a Hadoop file be written to receive complete mail message as object to be processed by its map and reduce operator. D. Processing. Once we have a scalable environment to store all types of data from different sources that may be of interest, we need a tool to process and analyze terabyte in a scalable manner, so we can achieve high performance. Apache Hadoop is an open-source framework used for large-scale processing of datasets on clusters of commodity hardware. It is based on the MapReduce model, a programming paradigm used to simplify the expression of parallelism. With Hadoop, all data is treated as key value pair. The programmer must be define a map function that may transform each pair. The runtime system then ground all pair with a same key and feed them as a list of reduced functions, also provided by the programmer, which may process the list as a unit. By design, all mapper and reduce may execute independently as soon as their input become available. Although Hadoop has been widely adopted by the security community in many specific problems, it is not adequate when the application cannot be directly expressed as MapReduce task. To handle cases where that is the case, our architecture also includes Spark, which has a more flexible programming paradigm. Instead of just map and reduce function, users have access to a large set of data operators that may be applied to datasets in parallel. A. Visualizing result. Finally, after executing all operations, the application must be able to present it in a human-friendly form. Different visualization platforms may be added to architecture easily using SDFS as a data repository, or by integrating them directly into the application. Our analysis use Python library, but other tools can be easily added. After architecture, we move to resolve. To illustrate the use of architecture, we present tasks that will be performed during the initial step of an analysis of phishing using our collect spam data. Experiments were conducted on a cluster of 10 machines, with one master and 9 slaves, performing storage and process functions. Each scenario was executed 5 times, and averages are shown, with bar indicating the standard deviation in each case. Each machine has 4 GPU, 8 GB of memory, and 300 GB of disk. A. Tuning, counting spam. Our first activity to evaluate the scalability of the solution under different configurations is a simple task: message count. More than the actual count, our goal was to validate our SDFS extension for mailbox and to understand how elements like data replication in SDFS, the programming environment, and the number of compute nodes used affect scalability. So we could find the best configuration for the cluster. We use both Hadoop and Spark version of the Cone application to assess the relative performance of the framework. For this test, we use message collect from February 2014. In that period, 93 million messages were collecting, totaling approximately 268 GB for an average 9.57 GB collect per day. Figure 2 shows the performance from the operation using Hadoop and Spark. It presents the execution time in minutes when varying the number of compute nodes. For both framework, the experiment using favors left result in the worst performance, taking 57 minutes to complete for Hadoop and 42 minutes for Spark, increasing to 5 machines. The runtime fall 36 minutes and to 5 and 1.5C and 1.68 times faster for Hadoop and Spark respectively using 9 machines. Hadoop running the time was 21 minutes, 2.74 faster than the 3-node scenario, and Spark was 14 minutes. Another interesting result is obtained when compare the sequential implementation. An efficient sequential program takes about 118 minutes to process all 268 GB of data, almost 8.7 and 13.17 times slower than Hadoop and Spark with 9 nodes, respectively. In all cases, we see that both Hadoop and Spark scale well in our scenario, although Hadoop is always a little below optimum speed up, and Spark a little above that. In that case, the superlinear speed up is due to Spark better use of caching in multiple levels of system. This result shows a potentially of the solution on scaling the number of machines and the replicability the real data. One important element in a large-scale storage system like HDFS is how it balances reliability and performance by creating multiple copies of the data. The HDFS replication factor can be configured by the user, and this affects both the reliability of storage as the reading speed. Using replication, HDFS tries to satisfy a read request with a block replica that is closer to the requesting node, and we can see that with 2 copies of the number of non-local access already dropped markedly, to the point that a further increase in replication does not provide visible effect in execution time. User must consider, however, that the system reliability is further improved with 3 copies of each file block. Hadoop divides data in file split that are read completely by SOMAPper. The granularity it used to define split and assign them to node is limited by the scheduler. On the other hand, Spark sees the field as direct mapping of a distributed data structure that it can handle just as it is laid across the compute node. That difference in approach makes its scheduling of computation more efficient in terms of data location, causing very few non-local access, one of the reasons for Spark better performance with more copy. B. Counting spam per reception. Counting message is basically a direct access application, since it just has to read data from storage once and count the object found. Another operation that makes a more elaborate use of the architecture is to count the number of spam that will be sent to each reception in our data. In that case, email from the mailbox must be read by the record reader, grouped by destination address in the header and then count. That operation map directly to the map-reduce execution model in Hadoop, and can be easily implemented by a reduce by key operation in Spark. One important element in both Hadoop and Spark is the configuration of the system to make sure it makes the best use of the parallelism in its execution. In Hadoop, the user must set the number of redos it will use. Spark, on the other hand, may be configured with the number of partitions it must divide the data into before processing, and that is related to the total number of file blocks involved. This experiment intended to check how sensitive each framework was, not their configuration parameter. C. Phishing identification. For our phishing application, the first step to identify phishing campaign is to differentiate phishing message from the other type of spam. Since our dataset contain all kind of spam message, in general, phishing attack attempt to steal sensitive information of the victim, such as password, credit card number, among others, trying to convince the user that the message is legit. Our method uses natural language processing technique to identify key features of each message through the generate score, enabling the identification of a phishing message by its differential score. Those features are discussed as follows. First, direct message. The first feature of our method is verify if the message is a message addressed directly to one person or if it's a generic message sent to more people. Identifying this feature helps in the phishing identification. 2. Mention of money. One way often used by attacker to convince users to reply their email is to promise easy money. Once the victim believes that that email is legit and that exists the chance to get free money, they usually answer the message, sending their information. Considering this characteristic, we analyze the whole content of the message under the identity mention of money, trying to find words such as money, cash, dollar, among other, and any money-related amount. 3. Sense of urgency. The phishing attacker tries to induce the victim to answer the message as soon as possible. One of the reasons is that when a person is under pressure or an urgent situation, it usually lacks the logical reasoning, tending to make hasty decisions. This feature is identify is or test if the content of the spam present any word with a sense of urgency. The set of words to consider what create using some keyword such as urgent, immediate, desperate. 4. Reply request. If the phishing attack intends to obtain sensitive information from the user, it will only happen if the user answers the message. Thus, the attacker tries to convince the victim to reply to the email. Here we also use to set a word create using WordNet based on keyword like reply, respond, answer, contact, edge. If the message presents 3 of the features described above, we consider it as being a phishing message. Once we analyze the whole set of spam, the next step is to detect phishing campaign in select message. We implement the operation described above using Spark and perform the execution on top of the same cluster as used in the first 2 experiments. In this case, we use only spam with English content. The data was collected using honeypot located in Australia, Brazil, Chile, Hong Kong, Netherlands, Norway, United States, and Uruguay. From April 2014, the dataset is composed by 19 million emails, totaling around 60 GB. Our result highlight 212 phishing campaigns with a total 700,000 messages, representing 44% of the spam. On average, each of those campaigns have 3,000 emails sent by 1.71 different IP addresses present in 144 and 1.26 autonomous system and country code, respectively. The biggest campaign found present more than 57,000 messages sent by only 2 different IP addresses from 2 distinct access. Figure 5 presents part of an sample extract from that campaign. All other email samples from that group are similar to this one. As can be seen, the attacker tried to confine the victim that is legitimate message from a bank and tried to induce the victim to access his bank account to steal his information. Despite the message appearing legitimate, we can see that the URL is not from the bank in question, but a fake created to device to the victim. In order to evaluate if our method was able to correctly classify the message into phishing campaign, we evaluate manually all campaigns generated. From the 212, only 4 were incorrectly classified, an accuracy of 98%. We are currently researching other rules that can be used to widen to set a possible phishing campaign that can be identifying by our system. Okay, after that we move to relate work. Several studies have proposed parallel and distributed solutions for network security problem. Using Hadoop, for example, Franquest et al. Proposed a scalable solution called bot cloud. Regarding the spam detection problem, Caruana et al. Evaluate the use of Hadoop to spam filtering, showing that their approach is scalable and efficient. Considering phishing, Marshall et al. Proposed Phishing, an automated phishing detection system using Storm. The system uses URL feature in order to identify the one that can be considered as phishing. LARX is another parallel and efficient anti-phishing solution. It extracts the URL contained in the network trace and checks them for phishing using Google Safe Browsing API. Even though we implement an application related to phishing and spam problem, the proposed architecture can be used to build applications to fight different cybersecurity problems. Conclusion and future work. In this paper, introduce an architecture that enables the implementation of big data application to be used in the context of cybersecurity. As the case study, we developed an application that aims to process spam traffic using HDFS, Hadoop, Spark, and data collect from honeypot spread in different locations of the world. We were able to demonstrate the power of our application, from the implementation of simple operation to be used in the analysis of spam traffic to more complex operations such as phishing detection. Experiments show that our method can correctly detect phishing campaigns, presenting an accuracy of 98%. Regarding the performance of the application, we obtained a speed up of 1.7 and 13.17 for Hadoop and Spark, respectively, using 9 machines. We also note the importance of replication in data locality and its consequent gain in processing latency. So, our architecture is effective to apply massive processing strategy in real applications that are sensitive to scalability. Okay, my review about this journal has done. Hope you enjoy it and thank you for watching.